person is waiting on you, Camilla. Are you sure, bruh? Oh, you're good.
Awesome. Thank you. Okay, guys, so we can get started, okay? Okay, so before we start, I just want to make sure that everybody knows I haven't seen Dr. Fraser's exam. I have no knowledge exactly what's going to be on there except for what he said in class. So, this is just kind of like a rough study guide, but you guys should definitely go back and look through your book and look through other problems. Some problems might be on the test, some problems might not be on the test. It's just what it is, okay? So let's start with number 1. So what do you guys think this one is? How would you start? Draw what? Okay, awesome. Oh, let me know if you guys can read something and I'll redo it. Okay. So what do you guys think that is? Constitutional? Okay. Does everybody see why? Right. So constitutional isomers, what are constitutional isomers? Yeah, go ahead. You can just shut it out. Right, exactly. They're arranged different, but they have the same formula, right? So what would be the formula for this one, guys? Right, but we're going to do it just condense it more, right? Because we want the molecular formula. One, right? Yeah, awesome. Everybody go on that one? 1, 2, 3, 4, 5, 6, 7, 8. Okay, yeah, it's 8. That's okay. All right. What about number 2? So it says, considering atoms with no formal charge, which statement best describes the valence of carbon, nitrogen, and oxygen? So, we're assuming that there's no formal charge on this. So how many bonds can carbon have? Right? So we can pretty much just pick from that alone. Right? Right. But if we had another choice that carbon had 4, how many bonds would oxygen have while it's neutral? 2? Okay, and how many lone pairs? 2. Awesome. And then I guess nitrogen? All right, so carbon is 4, oxygen is 2 bonds, 2 pairs. And nitrogen is what? How many bonds? 2 and 2? Nitrogen? There you go. 3 bonds and 1 pair. Awesome. Okay, so in ammonium, nitrogen has a valence of 4 and 0 non-bonding electrons. What is the formal charge of this? So what would you guys first do? We would actually have to draw to see what's going on, right? So it has 4 bonds. How many valence electrons is nitrogen supposed to have? 5, right? So it's supposed to have 5 valence electrons. How many is it showing here? 4, right? So what's the charge? Right, awesome. Okay. So which ones of these, awesome. Which ones of these molecules does the oxygen have a charge of +1? So we gotta do the same thing, right? So we said that how many valence electrons should oxygen have? 6. Oxygen should have 6 valence electrons. Okay, how many does it have in this first one? 8. So this one would be a charge of what? It has 2 extra electrons, so. Wait, hold on, does it really have 8 though? So like, let's look at it, right? So we draw the bond, H, H, H. How many does it have? Right, so what's the charge on this one? Okay, good. What about for the second one? Oh, crap. Can you guys still see it? Yeah, okay. No, you turn it off. Okay. How many is this one? So it's 1, 2, 3, 4, 5, 6, 7. So it should have -1. This one, how many does this one have? Right, so it's 1, 2, 3, 4, 5. So what is that? +1. Yeah. And then this one has 1, 2, 3, 4, 5 +1. So which one is it? Right. Everybody good on that one? Any questions so far?
Let's do that.
Okay.
And
That works out better
if it
anyway.
blinds you,
Yeah. No, that's fine because it was just like right in my face.
all right, just. So
Thank
wanna
you.
point it over?
No, it's fine.
All right.
Right there's perfect. What?
All right, there you go.
Oh, thanks. Okay, guys, so the hybridization for this one, what is the O? How do we get hybridization for each atom? Right, so the steric number, yeah? So how many sigma bonds does the O have? Anybody? Not one? Okay, good, yeah. Okay, so it has 1 sigma bond, and then how many pairs of lone electrons does it have? 2, right? So my steric number is 3, so it means that my O is what? Awesome. What about my carbon? How many sigma bonds does it have? Does it have any lone pairs? Right, so what is it? Right, because what's the steric number? 2, right, so it's sp. So which one can we automatically like take out? So, right, we can take out C, we can take out A because it says oxygen is sp and it's not. Okay, what about nitrogen? How many sigma bonds does that have? Sigma bonds, 2, okay. What? Oh, okay, yeah. Yeah, so what is it? Awesome. And then this carbon, the last carbon on the end, sp3. So what is it, guys? Okay. Everybody good on that one? Okay. Okay, number 8. So which one is our correct resonance structure? What do you guys think? Shout it out. Huh? Okay, so we gotta move the electrons, right? We gotta see where like the electrons can go. So we know that there's a lone pair here, right? So we can move this pair over here, but if I move that pair there, where would I have to move this pi bond to? To this carbon right here, right? Because if I leave that pi bond there, like my carbon's gonna have 5 bonds and we don't want that. So which one is it? B, right? You guys see why? Does everybody see why? Yeah. If I go too fast or anything, just let me know, guys. So, Can everybody see it? Okay, so we know that there's a lone pair there, right? So if I move this lone pair down here to form a pi bond, I can't leave this pi bond here, because then this carbon will end up having 5 bonds, right? So I'll have to move this pi bond to this carbon where it can take it, which means that I'll end up having a pi bond there because of these electrons. And then I move my electrons over here, which gives a negative charge here. Because how many valence electrons is carbon supposed to have? How many does it have here? 5, right? So that's a negative 1 charge. So if we look at the option right here, that's what it's showing. Oh, and also for the nitrogen, right? How many bonds does the nitrogen have? How many valence electrons is it showing here? Oh, crap, sorry. Yeah, how many valence electrons is it showing here? 4. And how many is it supposed to have? Right, so that's a +1. So then that's why this one will be, because like, this one will be it, because this one has a positive charge, the pi bond, and then the negative charge is on the carbon. Good? Yeah, okay. So, 8, 9, 10. So another resonance question. So which one is the resonance structure of this one right here? So I have a pi bond here, right? Can I move those electrons? Just up here. Which one can we automatically like take out without even like start doing resonance? Right? Because this one is adding an H, and we don't make new bonds or break any bonds. We're just, right? Okay. 4 is out, okay. So if we're moving the electrons up here, and now the oxygen, how many valence electrons does the oxygen have now? Oh, sorry. How many does it have now? 7, right? So now this is a negative 1 charge. And my carbon lost that pi bond, right? So how many valence electrons is it showing now? 1, 2, 3. Supposed to have 4, so that's a positive charge. So B. Everybody good with that one? Awesome. Oh, where did I leave? That's that. Okay. Okay, guys, so which one's my acid? This one? And my base? All right. So this one has to be my what? CB, and this one has to be my, okay, so which one is it? So 1 is acid, 2 is base. So we already know B or C are out, right? And then this one, my 3 is my conjugate base, so has to be D. Yeah? Everybody good on that one? Okay. So what is wrong with that arrow, guys? See? When we're drawing arrows, where should they always start? Where? Right. And the electrons, right? Because whatever we're showing with the arrows is the movement of electrons, right? Okay. So it should start here, because that's where we have the electrons. It should end at the H. Awesome. Okay. Everybody good on that one? Any questions? Let me know if I'm going too fast. Okay, can we name this one? So what is our first step for naming? What was it? Right, parent chain. So what is it here? Oh, sorry guys. No, just let me know because I forget. Okay. So like that. So that's 1, 2, 3, 4, 5, 6, 7, 8. Yeah? Okay, so that's going to be a heptane. Where would I start numbering my substituents? What? Oh, sorry, yeah. Thank you. Okay. Where would I start numbering my substituents? Right. Now I have an issue. Right here I start at the same, like my first substituent is at the same position, right? So what do I look at next? This one, right? So I'm going to start here. 1, 2, 3, 4, 5, 6, 7, 8. So that way this substituent is on position 4 as opposed to 5. Okay, so what would that be? Awesome. What is the common name of the following substituent? What do you guys think? How many carbons does it have? 4. So it has to be, right, so this one is out already. Where does it start? Sec, right? So secondary butyl, so it's D. What would a third butyl look like? Right, exactly. All of them would be connected, but it would still be 4 carbons. Okay. So another naming one. I'm going to skip this one unless you guys really want to do it, just because we just named this one. I just put it for extra practice for you guys. But there's some problems at the end that I really want to get to. So are you guys okay with that? Awesome. Same for this one. Is everybody okay with me skipping this one? Yeah. 14, let's see, and 15 is B. And actually I have the key here, guys, so after like the review is over, you guys can even take pictures. I might post it on the website. I haven't decided yet. Okay, so we're done with this one. So now this one. Okay. So we got to draw the Newman projection from this one, and we're looking down at this carbon, right? So we're looking at this carbon. What's on my left side? What's sticking out? Right, so I have a carbon here. What's sticking out? Huh? The methyl, right? And I have on top, I have my ethyl group. So I have an ethyl group. And then obviously we know that we have an H there because carbon should always have 4 bonds. So we have the H there. And then we can draw the one in the back. So the one in the back up top going into the page is what? Another methyl, so that's going to the right. And then down I have another ethyl group. And then I have another H going to the side. Right? So that means that it's C. Everybody good with that? Yeah. Do you want me to like dry it and everything? Yeah, okay, I can do that. Right here. Okay. So my arrow is right there. Yeah? Everybody's good so far, right? So I just redrew the, okay. So if I'm looking from down here, this is my front carbon right here, right? Is everybody good with that? Okay. So that's my carbon, and there's just a little period in the middle that represents my front carbon, right? Okay. What is going up? Ethyl. Okay. The wedge. What does my wedge mean? Like if we're looking at a page, is coming in or out? Out, right? So I'm gonna just do something here real quick. So if this is my molecule, right, and it's going in the page, and I'm looking at it from here, where is my methyl group at? On my left side, yeah? Okay. So I have a methyl group, and then, oh, sorry. And then I have an H on the right side, right? Because it has to have 4 bonds. Even though we don't draw all the H's, we know that it's there. So we know the H is on the right side. So now we draw our little circle. Yeah. Okay, so same thing. So if I'm looking at my molecule from here, right? What's going this way? Like, is my wedge or dash going that way? Right, okay. So my methyl is going to be here. What's down? Okay. And what do we know it's up here? Right. Is everybody good with that one? Yeah? Okay. Let me know if you guys have questions. Or if I go too fast. I won't bite, I promise. All right, so what is the most stable conformers of the 1-ethyl-2,4-dimethyl cyclohexane? So what do we know are the most stable positions when we're in the chair conformation? Where do we want them to be? Axial? Equatorial, right, yeah. Most stable is equatorial. And we want our bigger groups in equatorial position so that it's more stable, right? Okay, so just by looking at this, which one can we already see that is going to be the least stable one? Oh, sorry. So this is supposed to be 1, this is 2, this is 3, and this is 4. Yeah? So which one's the least stable one? 1, right? Because they're all in axial positions, right? So we already know that has to be the least stable. So I can just make a little note here, least stable. Okay. Which one's going to be my most stable? Following the same thought process. 3, right? Because that one's in, like, all of them are in equatorial position in 3. So most stable. Okay. So which one can we, like, so do we have our answer already? Yeah, it's A, right? But we can, like, look at this ones too. So we have 1 that's in equatorial here and 2 in axial. But which one is bigger? The ethyl, right? So that one we want it to be in equatorial for it to be more stable. So this one would be, like, we're just confirming our answer basically. So yeah. Everybody good on that one? Okay. How many chiral centers does this have? What is a chiral center? Okay, 4 different groups. So would this one be a chiral center? No, right, because this one has 2 H's there. Okay. So I'm counting and I'm seeing 1, 2, 3, 4, 5, 6, 7, 8. So D? Everybody's good with that one? I'm not counting that one, no.
Yeah, so you're not counting that one because there's 2 on the right.
What do you mean? There we go. There is an exception to this, guys, but I'm not sure if he talked about it in class, so I would just ask him in his office hours if you guys are like want to be 100% sure. Huh? He does. You just you just have to wait for him sometimes, but he goes. Oh, really? I'm sorry. Okay. So, number 1, is that cis or trans or neither? Huh? Okay, so when we're looking at cis or trans, what are we looking at? So it's like similar groups, right? Does this one have similar groups across the pi bond? So let's see. This carbon should have 4 bonds, right? So it has 1, 2, 3. So it should have an H here. And 1, 2, 3. So it should have an H there. So does it have the similar groups? Has 2 H's. So that would be trans. Well, what do we use E and Z for? Go ahead. So it's like when we have completely 4 different groups, right? Yeah. What about number 2? Which one? Neither? Okay. Everybody good on that one? So that would be B? Yeah.
Okay, so you said for the chirality center, it has like 4 different things connected to it, and doesn't have any like lone pairs don't count for that.
I'm not sure about that one, to be 100% honest. Yeah.
18 didn't we just say that for something to be a chirality center, it's just like 4 things are connected to
Right.
it, and lone pairs don't count? Are they lying?
No, they don't.
What do you guys think?
Yeah, it doesn't have to be like 4 different groups attached to the carbon.
Like I said, I'm not 100% sure on that one. I can definitely email him and then I can post it on the Facebook group if he ever gets back to me.
I was
Yeah.
not sure about that. And then why did we say that the double bonded that comes off, and there's like the O double bond, why did we say that wasn't one? Something about a pi bond or something?
This one?
No.
This one?
Yeah.
That was another question mark.
Uh,
Yeah. But I do have the answer key for this one. So I know for sure it's not a chiral center. Yeah.
and then
But can't you just think of it like as if it's attached to that carbon, like
Right,
and
yeah.
it's counting twice?
That's what I would think.
Like, just
I would think it counts as twice. But I know, I've also like, because I was reading on it and I was like looking it up, like it varies because sometimes it has to do with symmetry. So if it has a double bond, but like it has completely different groups on like all 4 sides, then it can count as a chiral center. But this one didn't for sure. So yeah.
and then trans is that they're similar on opposite sides,
Trans is on opposite sides.
and then cis is the same thing.
Right, for similar groups. So that's different for E and Z, right? Because we said E and Z is when we're looking at completely different groups across all sides. And then that's when we have to like give priority to see which one we look at and how we compare them. Yeah? Okay. So we said this one was B. Okay. What is the relationship between this one? Sorry. Enantiomers? Okay, so when in doubt, like this is what I've always been told about this and even the book. If you're not sure what it is, name it. Because if it's named the same, then it's the same molecule, right? Can you guys name this one real quick? So we have 1, 2, 3, 4, and it's an alcohol, right? Where's my alcohol? In a second, okay. So how would I name this alcohol? 2-butanol, right? And like the only difference would be whether or not they're R or S. What are they? Are they R and S? Are they the same, different? So this one is 1, my first priority. Second, third, I have an H. This is R. 1, 2, 3, I have an H. So this is an S, but because we have the lowest priority on a wedge, it flips it, so it's an R. So they're both R2-butanol. So they're the same. And like if you rotate it too, like you'll see that you can superimpose them and like they're exactly the same molecule. But some people like have trouble with like rotating molecules and trying to visualize it. So that's why I always say just name it and then you'll be able to tell for sure. Mm-hmm. Yeah. Do you want me to do that again? Because I went kind of fast through that. Okay. Right. Yeah, that's fine. So I'll just erase this. So this is my first priority, right? Since my OH is inside, my H has to be coming out. This is my second priority. Third priority, we said this was an S. And like what we always said, if your lowest priority is on a wedge, or what did you call it? A hatch? Yeah? Okay. I never heard that. Oh, this one? No, this one? Yeah, right. So my OH is on a dash, but my H is on a wedge. So when my lowest priority is on a wedge, I just have to flip what I assigned to it, right? So that's why we had S, but because it's on a wedge, we flip it to R. And they're both R2 butanol, so they're both identical. Everybody good? Okay, so if I have time, we can definitely do that at the end. Because like I said, I do have like some really good questions at the end. Yeah. But this is on chapter 5, I believe. So take a look at that. And there is a pretty cool, very simple chart, I know for sure, that says like, this is what each one is. So if you look at that chart, I'm sure it's gonna like, you know, okay. 21. Okay, so now we're doing the reverse, right? So here we named this one. Now we're coming up with a molecule. So if it's a pentanol, how many carbons does it have? 5. Can I like automatically take one out? Okay, why? Because it's a cyclo, right? Exactly. Okay, which other one can I take out? D, okay, why? Too many carbons, okay, so we're between these two. So let's just draw it. So 1, 2, 3, 1, 2, 3, 4, 5. Okay, our oxygen is, our alcohol is on 2. So it has to be R. And I feel like we just did this, guys. But okay, so then this one is 1, 2, 3. So this one is R. So and we need an R. So in order for that to stay R, we have to make this one on a wedge. Because if I put it on a dash, then my H will be on a wedge, and then I'll have to flip it, and we don't want that, right? Okay, awesome. So it's which one? Why? Good job. Right. So when I drew it here, I drew it on the left side, right? So I just have to flip it. So when I flip it, when I rotate my molecule, right now it's sticking out, but if I turn it this way, it's gonna go in now. Yeah? Does everybody see that? Everybody good with that? Which one? These two? No, they will be the same. Yeah. Yeah, but like I said, so I just drew it on the left side, so that's why it matters, yeah. Yeah, you're right. Yeah. So yeah, so this used to happen to me, and I've noticed like it happens to a lot of people. Like sometimes when you just see wedge and dash, you automatically think they're enantiomers, but that's not necessarily the case always, right? As we've seen, it depends on like how we're drawing them, if we're flipping them. So to always be sure, I would just name them and then assign chirality, and then that's how you'll know what kind of relationship they'll have. And there's another problem that's coming, so we can go through that. Yeah. Do you guys really need another naming one? Okay, so let's do it. So what is my parent chain? 1, 2, 3, 4, 5, 6, okay. Where would I start? So it's a hexane from here. So 1, 2, 3, 4, 5, 6. So what are my groups? 2 methyl, 3 ethyl, and then we can just assign the priority, right? So which one's my first priority? This one? This one? Yeah? Okay. Okay, so why? So they're all carbons, right? So we don't have any other atoms that are like can give us a higher priority. So we just gotta keep moving further and further apart until we can get our highest priority. So we start with this carbon. All the groups connected to it are carbon. So we can't really look at this carbon. This is a carbon, carbon, carbon. Yeah? So we gotta move one step further away. So if we go to our second one, so we have one carbon here, one carbon here, one carbon here. What is this carbon connected to? So it has a C and an H and an H. What is this carbon connected to? Carbon, carbon, H. Yeah? And then what is this carbon connected to? Carbon, H, H, which is the same as this one, so this is my first priority. Yeah? Okay, second priority. So at this point we're at the same place, so we go one further. What is this carbon connected to? A carbon, a hydrogen, and a hydrogen. What is this carbon connected to? 3 hydrogens. So which one has a higher priority? This one? Got messy, so I'm just gonna redry, guys. So we said this one was 1, this one was 2, this one was 3. And where's my last priority? Can you guys see it? Can everybody see it? So I do have an H there as well. That's my last priority. So if I assign to it, it'll be an S. But where's my lowest priority? Right, so I have to flip it, so it's an R. Right? You guys good? So which one is it? B? Awesome. Okay, so this is the one that I was telling you, right? So this is the other question that says, let me just bring it down here. Yeah. To identify, what do you guys think it is? Enantiomers? Okay. So what did I say is the like foolproof way to know what relationship it is? Assign chirality, right? Okay. So I have a chiral center here, 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 and here. So what is it here? I have my drawing here. Oh, perfect. Oh no! I'm so sorry, guys. Aside. I don't know if you guys noticed, I suck with technology. I'm so sorry. Oh, there it goes. Just kidding. Thanks, dude. Okay. So my first priority is here. Last priority is here. Yeah? I'm just going to assign chirality so I can see what relationship they have. That's all I'm doing. So which one's my second one? Okay. 3, so that is S. But where's my lowest priority? On a wedge, so it's an R. Okay. So this one's an R. Hold on. Can you guys see that? Okay. What about this one over here? So first, second, where's my third one? Oh, sorry, fourth. I always, so I always have a process the way that I do this. I always assign first and fourth because I see that those are always the easiest ones to assign, right? So it's just, I'm on like systematic here. Okay, so which one's my second one? And I'm gonna erase these. Can I erase these, guys? Everybody got this? Okay, cool. Okay, so 1, 4. So which one's my second one? The one on the left. 4, 2, 3. So that is. Yeah. So, okay. That's okay. I'm going to like redraw it bigger because now it's going to get really messy again. I didn't finish, but I guess it's S. Yeah, because where's my lowest priority? So it's already on a dash, so I don't have to flip it. So it's right the first time. Okay. So we already said that this one was an R. Okay. And again, if I go too fast, guys, just slow me down. I don't mind. Yeah. Okay. So which one is my first priority? Oh, right, because we do it by atomic number. So this one's 1. Which one's my fourth priority? Right, okay. Which one will be my second one? This one or that one? I have a different left than you guys. So like this one? Yeah. Okay. So we said this one's second one. Why? So again, we're going to do the same thing, right? So we're going to look at everything that's connected to this carbon. So we already saw that this is 1, this is 4. So we look at the next atoms that are connected. These are both carbons, right? So we can't really compare those because they have the same atomic number. And those carbons have the same groups connected to it. This carbon has an OH. Both of those carbons have OH and an H. So we can't really use those to compare them. So we have to move one further away. So if I go to this carbon, what does this carbon have connected to it? Right, this one has, so you guys should be able to see. Yeah, exactly. You guys should be able to see that that's an aldehyde. And that this is just an alcohol. Yeah? Because this has 2 H's there. We're going to have to draw those. So if we look at these carbons, which one has a higher priority? Right, because we count this oxygen as 2, right, because it's a double bond. So it has an oxygen, and a hydrogen. This carbon has 1 oxygen, 2 hydrogens. So by atomic number, this is the second priority because it has a higher atomic number than this one. Yeah? Everybody good? Okay. So 1, 2, 3. Let me just make sure. Yeah. So what is this? So if we do 1, 2, 3. So that's an R. Is that what I got? Yeah, that's what I got. So this is an R. Yeah? Okay. So now if we look at our last chirality center, so we'll put this is an R. So same thing here. So we look at what's attached to it. So this oxygen is going to take the first priority. Hydrogen is going to take our fourth priority. Which one's our second? So again, we look at what's connected to this carbon. It has 2 carbons connected to it, so we can't use those to compare because they're the same atomic number. So this carbon, again, has 2 oxygens and 1 hydrogen. What does this have? This has 1 oxygen, 1 carbon, and a hydrogen. So which one has an atomic a higher atomic number? This one? Yeah, so this one is 2, and this one is 3. So that is S. S, R. Everybody good with that? Yeah, okay. So I'm just drawing the second one. And I'm going to just do that one a little faster. Is that okay with you guys? Okay. Okay. Do you guys need me to like walk you through the steps, like saying this is 1, 2, 3, 4, or can I just give you the chirality centers? Okay. So I got S, S, R. So this is where we look at the difference, right? So what do we know are enantiomers? They're mirror images of each other. Are they mirror images based on chirality? So first, we need to make sure that we're looking at this right. So this right side is on this left side, right? Don't just look at it RS, RS, because this is the aldehyde here, which is over here. Yeah? Okay, so we have to be comparing this one with this one. So this is SS, so they're the same. So that automatically should say, okay, they can't be enantiomers because enantiomers have to be mirror images. So if this one was S, this one would have to be R to be an enantiomer, right? So enantiomer is out. They could be identical still because they have the same one. We go to the second one. This one is R, this one's S. So they're not mirror, but they're not identical. So, but they are like similar, so what can they be? So we said not enantiomers because they're not mirror images. Not identical because they should have to be identically the same like the name says it. They're not constitutional isomers, right? Because they're connected the same way, okay? They're diastereomers. Does everybody see why? You want to see the drawing again? Okay. I'll have it up here too, so like if you guys want to take pictures of this too, like they're all going to be up here. Yeah. This one? Okay, this one? I mean, we can go through it. I just did it really quickly, so, but we can go through it again. Okay. So let's check. So this is 1. This is 4. Which one's my second one? Right here? It is. It's an aldehyde. It's just drawn differently. Isn't this one your second priority? Oh, okay. I might have done it wrong, guys. Let me see. So, yeah, so this is an R. Right, exactly. Yeah. Everybody good then? So it was good? Okay. And I'll have these up here so you guys can take pictures. So yeah, so that's the main difference, right? So enantiomers, they have to be mirror non-superimposable images of each other. So they have the same connectivity, they have the same atoms, but like it's like your hands, right? How he always used to say, they're mirror images, right? But you can't superimpose them on each other. Yeah? A diastereomer, they're not mirror images at all. Like they have the same connectivity, but maybe like an oxygen is sticking out here while this one is going in. And that's how we have like the difference. But again, look at that chart on the book. That should clear it up really well. Everybody good with this one? Okay. So what about this one? So what? 2R3S dibromobutane is what? Okay, so what's our first step? Can you guys even tell what that is? Right, exactly. I mean, if you guys can do that without drawing it out, you guys are my heroes because I can't. So let's draw it out. So we have a butane, so we have 4 carbons, and we have 2 bromos on 2 and 3. So I just draw the bromos first, and then I'll see if it's to get the position, and then I assign whether it's a wedge or a dash based on chirality. So 2 is R. So I'm just going to number them like this. I could do it the other way. It doesn't really matter. So if I do 2, This is my 2, so it has to be an R. So in order to be an R, this is my first priority. I have an H there, right? Which one's my second priority? Okay. So second priority, this is my third priority. So if I keep it like that, that will be an R. So I can keep it like that, right? So I should put my BR on a wedge and my H on a dash. Everybody good with that? Okay. Then on this one should be an S. So this one is first priority. I have an H, which is my fourth. This one is my second. This one is my third. What's that? What is that? An R, right? But I have to make it an S. So I'm just going to put this on a wedge and put this on a dash so that it can be S. Okay, so what do you guys think so far? Is it optically active, racemic? I can't even say that. Dextrorotatory? I don't know. Or a meso compound? So optically active, it has to have chirality centers, but it has to be a chiral molecule, right? Is this a chiral molecule? You guys see it? If I rotate it, I'll have a BR, because this is on a dash. So if I rotate it, this will be on a wedge too, when I rotate it up. So I have an axis of symmetry. So it's a meso compound. Right? I mean, they have the chiral centers. So just remember, just because they have chiral centers, that doesn't mean that they're chiral molecules and that they're going to be optically active. Everybody good with that one? Yeah. Okay. All right. So I'm just going to like redraw it. Everybody's good on drawing it, right? Oh, hold on. I'll check it right now. Okay. Everybody's good so far? Everybody's on the same page that this is the molecule that we had to draw. Yeah? Okay. If I rotate this bond, right, I will have, my BR will stay here, right? But I'm rotating it. So if this one is going into my page when it's down and I'm moving it up, it's going to come out of my page. So it's going to be BR, it's going out. So do you guys see the axis of symmetry here? You guys see it? Okay. All right. So if we have a plane of symmetry, the book said that like if we have any kind of symmetry, it won't be optically active, right? So it won't be optically active because it is a meso compound. That's on chapter 5. Yeah. So I'll put it there for you. Everybody good? Yeah. Yeah, go for it. Mm-hmm. So whenever you're looking for, whenever you're doing these, right, you always have to see if there's any kind of symmetry, like between the molecules. So you should be able to visualize, or you should visualize them to see every different way that they can be. Because like we said, sometimes just the way that they're drawn differently, but that doesn't mean that they're going to be enantiomers, diastereomers. You have to like go through the whole process. So I was just looking for a plane of symmetry. Yeah. Yeah, and a sigma bond. So like, what about this one, guys? So like, if I have this, I'll bring it down. Does that have a plane of symmetry? But I can't rotate anything there, right? Because it's already in a, yeah, okay. So it's the same thing. Yeah, right. But this one I can. So just recognize those things, guys. Yeah. I know it's kind of hard to visualize until you guys get used to it. It was hard for me too. Okay, so do you guys need me to assign chirality here? Let me see. Yes? No? The answer is B, just so you guys have it, so you guys can like compare if you guys got it wrong or right. But I feel like we just did a bunch of these, so I don't really want to waste more time on that. Okay. What about on the Fisher projection? That one we can do. So we know that anything vertical is a dash or a wedge? Dash, right? And then horizontal is what? Right. So I'm just going to put my H on a wedge. My OH is going to be a dash. So this is 1, 2, 3, 4. This is R. But my lowest priority is on a wedge. So I'm just going to flip it. So it's B. Right. Yeah. So vertical is always going to be a dash. And like horizontal is going to be a wedge. Yeah. So that's why whenever you have an H on a horizontal, which most of the time you should flip it. Because you guys should be able to recognize that since it's on a horizontal, there's a wedge. Yeah.
That's why I don't understand 26 because for 2 I got that it was in R, but then since H was on a wedge, it became an S.
Okay, we can assign it. So this is 1. I don't even think I did this one. Okay.
Why wouldn't the right side is all that?
Do I still need to do it? No? Okay. Awesome. Let me know. I don't mind. Okay. So we're done with this one. Okay, so which of the following is an energy diagram for a 3-step reaction? So which one is it, guys? A or B, right? So what represents my intermediates on an energy diagram? The bottom parts, yeah. Okay. The troughs, yeah. Yeah, I know. I call them the minimums, the bottom, whatever. But everybody gets it. Okay. So this is my intermediate. This is my intermediate. So what are my top ones? Right. So that means that that's how many steps it's doing, right? So B. Because in this one, how many intermediates do we have in this one? 1 intermediate. How many transitions do we have? 2, right? I'm sorry, I can hear you. There's not always intermediates, right? Because sometimes, like on an SM2 reaction, we just have transition steps. It's mostly based on the transition steps.
So for every step, there's a transition.
Right, yeah. You could say that. Yeah? Everybody in agreement? Okay, awesome. Okay, I feel like we just went over this, guys. What is a transition state? Okay, a local maximum on the energy diagram, right? What is an intermediate? A point on the reaction pathway that has a discrete lifetime. Because the intermediates, they actually when we have the materials that they're like they don't have any intermediates, we can really I don't even know how to say this. So like in an intermediate, when we have like an E1 reaction, we actually form the carbocation, right? And it actually exists for a certain period of time, so it can actually undergo rearrangement. On an E2, we don't have an intermediate, so that's why we can have rearrangement, because it all happens at the same time. So intermediate has like some time that it actually exists, and we can actually isolate it, yeah? So 31. Which one cannot be an electrophile? D? Does everybody see why? What is an electrophile? It wants electrons, right? It loves electrons. So if it already has a bunch of electrons, it's not going to want more electrons. Huh? Right, yeah. It donates electrons. So that's why Dr. Fraser had on one of his slides that we can think bases and electrophiles as kind of the same, right? No, nucleophiles. Just kidding. I had to think that went through. Electrophiles are like acids, and nucleophiles are like bases. Yeah? Yeah. Okay, good. Okay, so which pattern is this? What is it doing? Nucleophilic attack? Okay. Everybody good? Yeah, that was a pretty easy one. Okay. Which one is that one? Rearrangement? Okay. What is the main difference that we can tell when it's a proton transfer and rearrangement? What does rearrangement have to do with? Carbocations, right? Exactly.
Wouldn't a rearrangement just, you would just have to, like,
No, tell me, go ahead.
I can't think of the word.
Okay, so like, right. So in a rearrangement, it always has to do with carbocations, right? So we always want to have the most stable carbocation. So if a carbocation is in a less stable place, the carbocation itself is not going to move. So he always said that, right? The positive charges are never going to move. It's the electrons that are going to move. But by moving the electrons, the carbocation then is going to be placed on another more stable carbon. Yeah? Everybody good? Okay. Okay, so what is wrong with the following mechanism? Right. It shouldn't be pointing to the BR. Because where do we say the electrons, the arrows always start? At the electrons, right? Yeah. Did you have a question or were you stretching? Oh, you were just stretching, okay. So since this is the nucleophile that's attacking, the arrow should start over here and end over here. Yeah? Okay. So it's D. So 35. Identify the sequence of steps in the following reaction. So what do we have here? Proton transfer? What do we have here? So it is a proton transfer again. Does everybody see why? Yeah.
In the book,
Mm-hmm.
for the question that we just did for, it says never place the payload arrow on positive charge. That,
The tail is up here?
no, I was just saying, like, no, never mind.
No, yeah, go ahead, tell me.
No,
Are you sure? Because, like, remember, the tail here is not on the positive charge.
no, I was just saying, like, that's like that.
Yeah, because this one, okay, this is fine. Thank you for that. So this one is just representing that the group is leaving, right? So it's starting at the bond that it's breaking and the electrons are going to the water. And the water is leaving. And this is the main thing, like the tail should be at the nucleophile because it's showing the movement of electrons. Okay, what is the sequence here, guys? B, okay. So proton transfer, what is this one? Na, what is this one? Proton transfer, okay. So B. Another naming one, guys. Do you want to name it or just? Let me double check. Yeah, it's B. I just have it done already, so, but I can work through it. I just, like I said, there's more problems, so, like, we've been naming a lot, so I think, we can go to the other ones. Okay. 38. How many primary carbons are here? Yeah. How many? One? Okay, so what is a primary carbon? That has how many carbons attached to it? Right. So one carbon attached to it. Okay, how many carbons does this carbon have attached to it? It's this one, right? So that's one. What about this one? Two. What about this one? How many carbons does it have attached to it? One. Okay. What about this one? 1, 2, 3. So that's a tertiary. What about this one? Has two. 1, 2. Yeah. So that's not it. Do you guys see any other that could be primary? All of them have more bonds with carbons, right? Mm-hmm. Right, because what about this carbon right here? What kind of carbon is this? It has 4 bonds. It's bonded to an H, 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 but it's still only bonded to one carbon, so it's still a primary. Just because it's a primary, that doesn't mean it doesn't have the 4 bonds, right? Okay. Which of the following is a reasonable definition of a concerted reaction? So what is a concerted reaction, guys? Right, all of it happens at the same time. What's the other name that he has for this one? Unimolecular or bimolecular? Unimolecular, okay. So in case you guys see that on the test. So unimolecular, it's a concerted bimolecular. It's 2 steps, right? Okay. Everybody good on that? I'm sorry, I couldn't hear you.
Isn't it the other way around? Like bimolecular means 1 step because like an SN2
What do you guys think?
stands for bimolecular.
Is that what it is? No? Yeah. I just call it 1 or 2 steps, so like I just wanted to like clear that up for his test, but I'm actually not sure, so that's why I wanted to ask you guys. But I can look up on his slides what he calls it. He has it on the slides, for sure. So if you want to just double check and like be 100% sure, I know for sure they're in the slides. Yeah? Yeah. This is in the slides. Okay. What is it? Bimolecular is SN2. So bimolecular is 1 step. Unimolecular is more than 1 step. Everybody clear on that one? Yeah? Okay. Okay, so which one is not a substitution reaction? So what is a substitution reaction, guys? Just like a basic definition. You substitute, right? Exactly. You substitute one group with another. So am I substituting an A? B? No, you're not substituting, but it could be a step of a substitution, right? Okay. C? It could also be a step of a substitution. Can D be a step of a substitution? What am I doing on D? This is on your chapter 9, so there's like a 1 word that I'm looking for that you're doing to the alkene. What are you doing to the alkene with the groups? Exactly. Yeah, so all of these you could use it in substitution reactions, but in this one, it's the only one that is showing that you're adding something as opposed to substituting it. Yeah? Okay. So that one's D. Okay. So rank the following substrates from most to least reactive. What do we know is the most reactive for SN2? Before primary. Right. Exactly. So methyl, primary, secondary, and tertiary. So which one is it? So we know A has to be the first one. So B and D are out. Yeah? Okay. Then which one can be my second reactive? C, because that's a primary. So there we go. A is out, and we have C. Okay. Okay, so this one is a little bit different. So they're all the same, except for the leaving groups, right? So which one is my best leaving group here? No. I had to look that one up too, guys. Iodine is your best leaving group. Yeah. That's in your book too, though. That's in chapter 7. If you guys ever if you guys need me to tell you what chapter anything is on, just tell me and I'll tell you, because I do know which chapter it will be on for all of them. So my next one, which one is it? BR. Okay. So which ones can I automatically take out? A and D? Okay. So which one is it? B? Yeah. Perfect. Okay, now this is in an SN1 reaction. Yeah. So what do we know the order for most reactive to least reactive is for SN1? Tertiary, secondary, primary. Why? Right, yeah. Because in SN1, it happens concerted or non-concerted? Non-concerted, right? So we actually have an intermediate, which is our carbocation. So we want our carbocation to be the most stable. So, and we know that our tertiary is more stable than secondary. There's actually something else more stable than a tertiary carbocation. What is it, guys? Allylic, right, exactly. Benzylic allylic, okay. And what's less stable than a primary? Vinylic? Oh. Good job. You're on your way to Argo too. Okay. Vinylic. So if I have that, and that's my leaving group and that leaves, I'll end up with this. My carbocation is on the vinylic position. Everybody good with which one is vinylic and allylic? No? Okay. So if you have double bonds, so I'm just going to, this is my double bond, right? These will be your vinylic positions, and V, and these will be your allylic. They're one away from the double bond. The vinylic are on the actual double bond, on the carbons that are part of the double bond. Good? Okay. Everybody good now? Yeah? You guys are good? You guys are so far away. Okay, so which one is my order here? So which one's my most stable one? What do you think? Right, exactly. So this is my least. Which one's my most? A? Why? Right, exactly. So we can take automatically out which ones? Oh, it's A? Okay. So which one's more stable here? Right, so it should be A, B, C, D, which is what we picked. Awesome. So which of the following is a major product for the following SN1 reaction? So what do we know about SN1 reactions? Huh? Yep, intermediate, thank you. Intermediate. Okay, so what's going to be my first step here? Okay, so this leaves. So I'll end up with that. Is that my most stable carbocation? Where could my carbocation be? Okay, so I could just do a hydride shift, right? And then end up with my carbocation here. Is that my most stable that it can be in this molecule? Yeah? Okay, so that's where my nucleophile is going to attack, which is my water, right? So then I can just add my water here. Right? And then we'll end up with, yeah, and then that gets deprotonated. Yeah? So which one is it, guys? B? Does everybody agree? Everybody good? Yeah. So we have a water, right? So it's just going to come and grab the proton, and then that's going to stay behind. And then we have that. Everybody good? All right. Okay, so what do we know about stability for alkenes? What is my most stable alkene? Most substituted? Awesome. So most substituted is most stable. The double bond, yeah. So like we have the different functional groups, right? So if it's completely saturated, what kind of functional group is that? Alkane. Okay, good. And with a double bond is an alkene. What's it? A triple bond? Alkyne. Yeah, awesome. So which one is my most substituted alkene in here? B. Okay, so I can take out A and B already. So what would be my second stable? Between A and C, which one has more substitution? C? Okay, so has to be C, right? Everybody good with that? Okay. So if you have your alkene, right? The groups that are on this side, on one side and on the other side. So this is one that's completely substituted. It has 1, 2, 3, 4 groups. If you only have this, that's only 3 groups. So this one will be more stable than this one. Because this one still has an H, right? But that won't be stable as this. Like if this was all methyl, 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 methyl. As opposed to where like this one is 1H. That's on chapter 8, if you need to look at that, yeah. Okay, so what is the product of the following elimination? So what kind of base is that, guys? What is an elimination? Right. What do you create from an elimination? What? Alkenes? Okay, awesome. From just one elimination is an alkene, right? Okay. So, awesome. Well, if you have, not always, because like you can also make an alkyne by elimination if you have 2 halogens, but like the whole point is that you create a pi bond from an elimination, right? Okay. So what kind of base is this, guys? Bulky or small? Small, okay. So what product will I get? Answer sheet. Right. Which means that it's going to be what? The most substituted or least substituted product? Most substituted? So which one is it? So my leaving group is here, right? So where am I going to form my double bond? I have, how many alpha hydrogens do I have? Beta hydrogens do I have? Which one? A? Okay, why? So what does that have to do with antiparaplanar? Because what do we know about our sigma bonds? Right, they freely rotate, so they're not stuck in one position. So in a cyclohexane, we said that they can rotate, right? So they're stuck in whatever position. So they have to be in the position of antiparaplanar to the leaving group so that they can form the pi bond. Huh? Well, this one, no, because this one can freely rotate, so it can get in the position where it can actually form the pi bond. Yeah? Okay. So which one is it? See? Okay. Right. So we said, like, so it's a small base, so it's going to give us the Zaitsev product, which is the most substituted, which is right here. And it's just doing it with the beta hydrogen, beta proton, whatever. Okay. So we can, done with this one. Okay. So which one shows, which of the following shows a mechanism for a concerted elimination? Oh no, we're gonna run. Okay, so we're gonna run out of time, guys, because we still have a long way to go. So I'm gonna try to like rush a little bit more through it. If you need me to slow down, just let me know, okay? And I'll post the answer since we're not gonna get through all of it, okay?
Like the ones you'll work out.
I won't necessarily, no, I'll just put the answers. Yeah. Some of them, like the very last, that they have like that they're missing the reagents. I put the reagents, but I won't like actually like do the explanation how we're doing now. Yeah. Okay, 47. So which one is the mechanism for a concerted elimination? So what did we say concerted was? All at the same time. So which one is showing one that's happening all at the same time? A. Right? Because in this one, we have an intermediate. We have a carbocation, so that can be it. This one we're having, it's not happening at the same time. This is the only one that we have a leaving group that's leaving at the same time as the base is coming and attacking the H. Yeah? So what would be the best base for performing the following elimination? Third butoxide, right? Yeah, because we're forming the least stable alkene, because it's least like the one that has less substitutions. So we need a bulky base for that, and that's what this is. All the other ones are small bases. So what is the product for the following elimination? Okay, so this one is the one that you guys were thinking about, right? So I'm going to draw this one out because he really wanted me to go over this. Okay, so this is my one, so I'm going to put my chlorine up. My methyl is down, so this one is going to be on my second position and is going to be axial. So where's my only beta proton that I can do the elimination with, where I can form the double bond? So it has to be antiparaplanar, right? So since this position is already being occupied by the methyl, the H that I have to use is the one that's here. So then that will form my double bond. Right here. And my methyl is here. So then I just change it back to this. Right? Right. What position does the chlorine have to be in order to do elimination? Axial. Yeah. Oh, okay, sorry. I'll put AX. Yeah. If it's equatorial, it won't undergo elimination. And the same thing for the hydrogen, right? That's what antiperiplanar means. So the chlorine is axial up, my hydrogen is axial down, and they can go and overlap to form the pi bond. Yeah? Everybody good with that? What?
So interparaplanar means that they both have to be, they have to be opposite of each other, so that one has to be.
Axial. But they have to be in axial positions. Don't forget that. Right, because if they're in equatorial, you won't have elimination. No. Not that I know of. Yeah. I don't know what chapter it is. I believe how to draw, if you're having issues like drawing the chair conformations, I believe that might be in chapter 4. And then like the elimination ties it in with chapter 8. Yeah, but he keeps mentioning chair conformation, guys, so I will pay attention to that. Because even from the tests and the assignments that he gave in class, right? I'm just saying, like, he didn't tell me that that's going to be on the test, but I would imagine because he keeps mentioning them all the time. Okay, so which one is it, guys? What number are we on? It's going to be E, right? Yeah, because with this, our chirality center doesn't change or anything. We're just forming the double bond. Okay. So which of the following alkyl halides would afford the indicated product upon reaction with sodium methoxide? It's the same thing, right? So we have to draw it out. So 1, 2. So if this one is going up, my chlorine, and this one is going up, equatorial, that means it can form a double bond here or here, but that's not the one that we're trying to get. We're trying to get one away from the group, right? So that won't give me the product. Will B give me the product? Do you guys want me to draw it out? Yes? No? Okay. So they're both on 1. So, hold on. So remember, like, my leaving group always has to be axial, right? Yeah. So my chlorine is down. This group is equatorial up. So it can do, it has the option to do it here or here. But again, that's not what we want. Because if we do that, then my double bond is going to end up right here or here, right? We want it one away. So let's look at number C. Let's look at letter C. Okay, so 1, 2. So 1 is up, 2 is down, right? So where's my only beta hydrogen that I can do the double bond at? So if I like number them, I'll make it easier for you guys. 6, right? That's the only one that's antiperiplanar, right? So then it can overlap. Now let's look at my product. It'll be here, and it's 1 away from my, what is that? Isopropyl? 1, 2, 3, yeah. Is that what it's called, isopropyl? I think so. Yeah, right? Yeah, okay. So that was 1 away. So that's one product that's giving us a product that we want. So that's checked. And then D. So, what else are here? That was a horrible chair, guys, but it gets the point across. So chlorine in my first position is down, so it's axial down. My isopropyl is on 2, and it's up, so 1, 2, so it's going to be up. So again, where's my only beta hydrogen that I can have the elimination at? Right here. That's where we want it, because we wanted one away from the group. So it's both C and D, which is E. Everybody good with that? So that's the position, like from the living group where it is. So like it has to be one further away. Yeah, because like if it's further away, it won't form the double bond.
So how do you know if it's facing an S or everywhere?
So that's, so that, like I said, that's on chapter 4, and like that's where you learn like how you draw the chairs and what position, like where all the positions are. But they pretty much is just like on one, if axial is up, the next one is axial is down, the next one is axial up, and they just keep like going like that. So on this one, if my chlorine is down, then the ones right next to it have to be going up. But my group is already occupying the axial up position, so my hydrogen can be up, axial up in that one, right? Because it's already in that position, like isopropyl. But it can be here because I have no groups that are taking that. Does everybody see that? Do you want me to draw it again? No? Everybody good? Everybody good? Yeah? Okay. So we said that was E. So what about this one? So what are the steps in the following mechanism in correct order? So it's an elimination. Our OH is leaving, but we know that OH is not a good group. So what's the first thing that we have to do to OH in order to make it a good leaving group? Protonator, right? Or we can tosylate it, but that's not an option here. So A is out, B is already out, right? Right? So we have a proton transfer, then our loss of a leaving group, the water's gonna leave, right? So let's do it. Do you guys want me to draw it out? Okay. Let me know if you can see it. So you guys remember what this looks like? The H2SO4, when you draw it. It's just a source of hydrogens, right? It's just an acid, right? Yeah. So it has an actual way that you draw it, but I always just do it like this because it's just a source of hydrogens, right? Yeah. So if I'm going to protonate this one, this stays back. So then, now my oxygen has a positive charge, right? So it's going to leave now. It's a good leaving group now. So what do you guys notice about this? Oh, yeah. What do you guys notice about the carbocation? Right. It can be more stable than it already is, right? So what are we going to have? Right. So we're going to do that. And now it's here, and that's a tertiary, right? Everybody good with that? And now I can eliminate. And I'm going to eliminate just the H here. So then I can form my double bond. Does everybody see that? That's just like the regular elimination. This is the more important part. Just that you're having a rearrangement. Because like he says, he loves to say the driving force, right? It's always looking for stability. So we have a more stable carbocation, it's going to rearrange. Everybody good with that? Yeah. So it's just going to come here, and then the electrons are going to go here. And then I'm going to have my double bond. And that is my final product, right? Yeah, good. So what are our steps? So we had a proton transfer, we had loss of a leaving group, we had a rearrangement. God. again. Oh, there we go. Okay. So we had a rearrangement. So which one is it? Awesome. Okay. Which of the following is the product of the rearranged carbocation in the following dehydration? So it's the same thing, right? We're going to start with the same step that we just did before. We're going to protonate this oxygen to make it into a good leaving group. So that's going to leave. So we're going to end up with this carbocation. And again, what do we say about carbocations? It's going to try to be the more stable carbocation. So if the rearrangement can happen, it will, right? So we're just going to have another methyl shift again. And what do you guys think that will be then? B? You said B, right? Yeah. Okay. You guys good with that one? Okay. All right, so we have a lot to go, and I can post the answers for the rest of the multiple choice. I really wanted to do just some predictive product ones. Do you guys want to do that, or do you want to just get through the multiple choice as much as we can? No? The back? Okay. And I'll post the answers, okay? So 71. On the what? Yeah, on mine. Not on the study union one, but on mine. I have one. Yeah. Okay, so I know you guys' favorite. So what do you guys think we'll start with? Na what? Uh-huh. Okay, we can do that. So about synthesis, right? There's not one right way to do it because you can use different reagents that will give you different products. I'm sorry, guys, I'm so cold. So, and maybe you'll have one way of doing it, and then you'll have a different way. But as long as you guys are following the rules of the reagents, then we're good to go, right? From this one, well, this one can be a little bit of different ones. It has an alkyne, so an alkyne is chapter 10. Yeah, but 7 through 14. Yeah, it's a lot. But at the end, huh? Well, you should always try to shoot for the least amount of steps anyway, because, you know, like, that's less reagents that you have to remember anyway. So, and you want a more efficient synthesis, so yeah. Okay, let me see. Oh, yeah. So you said NaNH3, right, which will give you a what? Who told me that? That's a good one, because what does it do to the alkyne? An alkene, right? And what can we do to an alkene? Right, yeah. It's okay. So I'm going to show you guys the way that I came up with, but that's not a bad way either, because you could go from there. So if we have the H2 with Lindlar's catalyst. So it's kind of the same. You see that? Like I'm still bringing it down to an alkene, but I'm just doing a cis alkene as opposed to a trans, yeah. Lindlar's catalyst. Okay. So what does that give me? One, two, three, 1, 2, 3. And always count your carbons, right? Actually, that's, are we adding any carbons here? So let's count. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're not going to add any carbons. So we don't need any reagents that are going to add any kind of carbons to this, right? Because we have the same amount. All we're doing is we're just changing the functional group. We're going from an alkyne to an alcohol, right? Does everybody see that? Okay. So then if I have my alkene, I can make that directly by just doing BH3, THF, and H2O2, NaOH. Because what does that do? It adds the alcohol on the least substituted side of the alkene. Because if I had used the other one, the, what is it called? High mercuration, demercuration, that one, yeah. Yeah, that's the one. Then it would have added it on this side. And that's not what we want. We want it on the other side. Everybody good with that? Okay. What about this one? What can I make this from? So what am I adding here? So instead of one alcohol, I'm going to have two OHs. It's going to be a diol, right? So what reaction do you guys remember where you guys added two OHs to anything? Chapter 9. Remember how you made a diol from an alkene? There were like 3 different ways, right? There were 2 that you could do anti, and there was 1 that you could do syn, right? Okay. So I can make this from an alkene. And I can make this alkene from that by just doing elimination. Does everybody see that? So then I just put them together. I can do elimination with this. I remember we just did this elimination, right? That was the last problem that we did that I showed you. Then we add our OHs. Na. Everybody good with that? So if you guys are like still struggling a little bit with your reagents, I really recommend that at the very end of the chapters, they have like this little like clockwork looking thingies. Like that helped me out a lot. And like that tells you where you, like what reagents you're using for what. So at least you can recognize, and then you can like play around with the reagents. Because if you can see what functional groups are changing, right? Because when we're doing synthesis, that's basically what we gotta look at, right? We gotta see if the carbons are changing, and we gotta add them or subtract carbons, or if we're changing the functional groups. And then our reagents help us change our functional groups depending on other things. And let me see. Okay, so I'm gonna end with the last one. Synthesis. Okay, so what am I doing here, guys? Oh, I'm so sorry. Yeah. So let's start. So our first thing is, so let's count your carbons. Are we changing how many carbons we have? Right, so we have 1, 2, 3. We have 3 carbons here. 1, 2, 3, 4. We have 4 carbons here. So we have to use some kind of reagent that's gonna add carbons, right? And then our functional group. Is our functional group changing? What is it changing from to what? Okay, so is this a ketone? Okay, so where am I synthesizing from? Am I going from here to here or here to here? So I'm going from here to here, right? Because that's where my arrow is pointing. Okay, so I'm going from an alkyne to an alcohol, right? Okay, so what's one way that I can go from an alkyne to something that has an oxygen? Because that's an alcohol, right? So we can go back and think and say, okay, well, I have alkynes. What can I do to an alkyne? I can add halogens. I can add the hydrogens to bring it down to an alkene or an alkane. So you got to go back and think, what can you do, right? Well, if you bring it down to an alkane, can you do anything with an alkane? Right, because we have to kind of like almost activate an alkane, right? He said like an alkane is non-reactive, and that's what we do our radicals, so that we can add a halogen so that we can do other stuff to it, right? Okay. So, but what's one way that I can add some kind of oxygen to an alkyne? Huh? Right, we can do O3, right? But then that will give us a carboxylic acid. So then that's going to be really hard, because then that's going to give us 2. Yeah, okay. So there is one that we add an alcohol. Remember, like just in alkenes, we have the one, like the one we were saying, oxymercuration, demercuration, something like that, yeah. So that one, we add an alcohol at the most substituted side, right? And then we have the other one. Alkynes have the same thing. And you can go back and look at the reaction. That's in chapter 10. So we can just do HgSO4, H2SO4, and then H2O. What does that give me when I make that? Right, exactly. So it adds an alcohol, but remember what he talked about? That it undergoes a process what? Called what? It's a really weird word. Yes, exactly. Can you say that louder? Yeah, there you go. It tautomerizes, right? Like we add the oxygen and then there's an alkene right next to it, but then it all shifts around so that you end up with a ketone, right? So, so this I can make from a ketone. 1, 2, 3. 1, 2. Right? This I can make from that. Right? And then what can I do to go from the ketone to the alcohol, but also adding another carbon? Because to this, I haven't added another carbon from here to here, right? All I did was I added an OH, and then that turned into a ketone. What can I do to add carbon? Right, exactly, grain yarn. So I'm just gonna do a grain yarn right here. And then like how he says it, quench it, right? Yeah. All right, guys, so are there any questions? I do have to end at like 9:20. If anybody has any questions. Everybody good? Okay. And then also, so if you guys have like a minute, if you guys could fill out those surveys that I give you, I'm gonna like come around and collect them. Who didn't get a survey? It's just a survey for the SI session, for the review. Oh, okay. Yeah. Oh, do you need one? Okay. Did you guys get one? It's just a survey about the review session. So if you guys can just fill it out and like give it back to me when you're done, that'd be awesome. Thank you. Bye. Oh, thank you. Huh? Yeah. Oh, sorry. So yeah, guys. So I'm gonna post the answers. I'll try to do it by tonight,